Okay, there, now it's working. So, we're going to do this small assignment. It shouldn't take us very long. At the end of every section, there is a set that has true or false, catch the mistake, and some other problems. So, looking at number 103, what mistake did they make? Yeah, -3 times -2 is not -6. So there is the mistake. So you have 3 others that you'll need to catch the mistakes. And then the true false are kind of tough, so we'll do all of those together. So the equation 3x plus 1 squared equals 16 has the same solution as 3x plus 1 equals 4. True or false? Basically, it's saying x squared equals 16 is the same as x equals 4. False. Why is it false? We ignored the plus or minus. So that is false because there should be a plus or minus in there. Good job. 108. The quadratic equation ax squared plus bx plus c can be solved by the square root method only if b equals 0. False. You can always complete the square. Right? Right, so you'd have to convert it into a complete the square problem, which would allow you to do the square root method. Now, we're not going to do that when a is not 1. We're just going to use the quadratic formula. Okay, number 9. All quadratics can be solved exactly, meaning you don't have a decimal in your answer. So it's true. So there might be a little bit of a caveat here, but solved exactly means you use the quadratic formula and you don't convert the square roots to decimals. But what if the original problem had decimals in it? Of course, yeah. I think the answer is false, but I bet the book says true. Somebody look. Is this true? Yeah, I kind of disagree with that, because what if the original quadratic was an irrational decimal that you couldn't write? Now, when we say quadratic, we mean integer coefficients. So it is definitely true if the coefficients are integers. Whatever. I'm not worried about it. But do you guys see the problem? What if your original quadratic could not be written exactly because it was an irrational number? Now pi, we can write pi exactly. We just write the symbol pi and then pretend that we know all the numbers. But what if the quadratic had a coefficient in it that was an irrational number and we didn't know all of the number? Then we wouldn't be able to solve it exactly. But I think it's defining quadratic equations as having integer coefficients. And if all of the coefficients are integers, then yes, it can be solved exactly. 10. The quadratic formula can be used to solve any quadratic equation. That is definitely true. It's a beautiful thing. Okay, now, I don't know why they do this, but they do it in every single chapter or every section. Number 11 is not a true-false question, but it's under the true-false heading. But notice how it says exercises 107 to 110 are true-false. There are no instructions for 111 through 114, which is weird. So Write a quadratic equation in standard form that has x equals a as a repeated root. It's not a true... my son the other day, a couple months ago, we were talking as a family, and we said something like, "What would you say if somebody asked you to explain?" I don't remember what we were talking about. So, what would you say if somebody asked you to explain how you felt, whatever? And Scotty said, "No." What would you say if somebody asked you to explain all of this? I'd say no. Okay, so x equals a as a repeated root. What does that mean? What's the other root? It's also a. Okay, so what would that quadratic look like? Well, it would be x minus a and x minus a, and that would be x squared. Can you do that in your head? Minus 2a plus a squared. And that is the trick we use when we do complete the square. We take the middle term and divide it by 2 and square it to get the a squared term. Okay. It says alternate answers are possible because you could multiply this by anything, by any real number, and you would still have a quadratic that has a duplicate root of a. So you could times it by 5 or 9.2 or divide it by 100. Okay. Write a quadratic equation that has bi as a root. This is a little bit harder. So x equals bi, and what would the other one be? Well, can you have just one imaginary root? No. They always come in pairs, and those pairs are always conjugates. So if bi is a root, then negative bi has to be a root. Why? Well, I'm about to show you. So, x plus bi, or, well, I guess it doesn't really matter, but x minus bi and x plus bi. Watch what happens when we multiply these. X squared plus, oh, what order does everything go in? It does matter. Well, I mean, no, but we have chosen a specific order for everything so that everybody writes it down the same way. B is a number, right? X is a variable, and I denotes complexity. So numbers go first, then variables, then i's, and if we had a square root, it would go after that. So the order is always numbers, variables, i's, square roots. Okay. And does it matter? No, but if you do it the same way everybody else does it, and you do it the same way in every problem, the simplifying will be a lot easier. Minus bxi, and then what about the last one? Negative b squared I squared. Ah, good. So first off, bxi and negative bxi cancel. I knew that was going to happen. How did I know that? I was dealing with conjugates, right? X plus bi, x minus bi. Anytime you have conjugates, the middle term will drop out. Okay? And over here on the end, I squared. So I is defined as the square root of negative 1. So I squared would simply be the square root of negative 1 squared, and the square root and the squared cancel, and I squared is negative 1. So this becomes negative 1, and negative b squared times negative 1 is just b squared. That's why imaginary roots always appear in conjugates. Okay? So the only way for this to happen is to have conjugates, right? So if I had x equals 3i and x equals negative 4i, will the i's disappear in my multiplication? No. This will not happen, right? The I squared will still happen, but I will end up with a middle term that contains i's, and we only deal with quadratic equations that have real number coefficients. So if your quadratic has real number coefficients and it misses the x-axis, then your imaginary roots will always be a conjugate pair, 3i and negative 3i, plus or minus 7i. It does get a little bit more complicated. What if one of the roots was 2 plus 3i? What's the other root? It would be 2 minus 3i. And then you would have x minus 2 minus 3i and x minus 2 plus 3i. And you don't need to write this down, but watch what happens. X squared minus 2x plus 3xi minus 2x plus 4 minus 6i minus 3xi plus 6i, and then minus 9i squared. That was annoying. I never want to do that again. Watch what happens. 3xi, negative 3xi, negative 6i, and positive 6i. So the 2's go together, x squared minus 4x, and then I have a 4, and I have a negative 9i squared, which is really 9, and I get plus 13. Now, because of the conjugate rule, I can skip all of the i's except for one of them. Which I do I have to multiply? The last one, the I squared. So let me do another one for you. And we're going to be doing stuff like this in the future, so this is really good to know. What if I had negative 4 plus 3i? Then the other one would be negative 4 minus 3i. So my factors are x plus 4 minus 3i and x plus 4 plus 3i. And now I'm just going to be really smart. When I multiply these together, I'm going to skip all the i's except the last one. Do I need that? Yes. Do I need that? Yes. Do I need that? No, because it's going to have an opposite somewhere along the way. Do I need this? Do I need that? Yes. And that one? No. That one's going to cancel something along the way. Okay? That? No. That? No. That? Yes. And it's negative 9i, which is really plus 9. And then I get x squared plus 8x plus 25. Right. So anytime you have an imaginary root, it comes in a conjugate pair. And this is how you build the equation. Now, wait a minute. hopefully you just realize that you don't even need to write any of that stuff out. You can do all this in your head. Do you see the pattern? It's just x plus 4 squared and then an I component added on to the end. Right? 4x, 4x, and 16. You can do that in your head. And then the I component is really easy to do in your head as well. So if you want, what is this going to be? Well, it's going to be x squared and then 2 copies of my negative 5x. So that's negative 10x. And then this is going to give me 25. And this is going to give me negative 1I squared, which turns into 1. So plus 26. Now that might be a little bit of a jump for you, but as long as you remember, you can skip all the i's except for the last one because they're all going to disappear. And then you also know that something like this is just not going to work. You cannot create a real number quadratic using only those 2 factors because they're not conjugates. Okay? 13. Write a quadratic equation that has the roots 2 and 5. That's really easy. Can you do that in your head? X squared minus 7x plus 10. Okay, what about negative 3 and 0? What are the factors? Oops. You said it right, and then I didn't write it correctly. And what's the other one? We could write x minus 0, but it's just x. So x squared plus 3x. Okay. Is that it, or was there more? So, okay, 15, 17, 19, 21. Okay, so 15. S equals 1/2 gt squared, and we want to solve for t. What should I do? Well, let's look at t. What is the order of operations starting with t? And the 2 and the 3 can be flipped. Right? But the squared has to be first. So to solve, we're going to go in reverse order. How do you get rid of a 1/2? Times by 2 or divide by 1/2. So 2s equals gt squared. Divide by g gets rid of this. And then take the square root, and don't forget the plus or minus. Now, what if you divided by 1/2 and you had s divided by 1/2? How do I fix that so it's not so messy? Well, what's the rule of dividing by a fraction? Just flip and times it, as Tom likes to say. So we take s over 1 and we times it by the reciprocal of that, and I get 2s, which is what I ended up with. Okay. 17. A squared plus b squared equals c squared. Solve for c. I'm just going to get plus or minus the square root of a squared plus b squared. Now, that is the Pythagorean theorem. You did Pythagorean theorem problems for years and you never used plus or minus. Why is that? You only did them in a geometric circumstance, and you were dealing with triangles, and the distance was always positive, so you ignored it. Now, when you get deep into trig, if you take 1060, for instance, sometimes you'll take the square root of the side of a triangle, and you'll end up with a negative number. It can happen. But I guess it happened to you last year a little bit. Not a lot, though. Right? 19. X to the fourth minus 4x squared. What should I do? Take an x squared out, and then I get x squared minus 4. That's a difference of perfect squares. Good. X minus 2 and x plus 2. So what are my roots? 0, 0. Why 2 zeros? Because it's x to the second. Do I need to write both zeros? No. But I also have a 2 and a negative 2. What does this graph look like? Kind of a W shape, right? What does this do? It's a bounce at 0. So I have to hit negative 2 and positive 2 and 0, but I have to bounce off of 0. And because this is a positive, I know it's a W instead of an M. Does that make sense? So the W would have to look something like this. Okay. What if it was negative 2, negative 2, 0, 2? What would that look like? Would bounce at negative 2. So a bounce at negative 2, and then it would look like that. That's more like the W's I write. My handwriting is pretty bad. But W's don't have to be symmetric. And by the way, symmetrical, not a word. Yeah, symmetric. We call it symmetric. Okay, last one. 21. Ooh. Wonder if you guys remember how to do this. X to the third plus x squared minus 4x minus 4. So, there is a way to factor cubic equations. It must be really difficult to do because I've never learned it. Right? Bachelor's in math education, master's in math education, never learned how to do it. From what I understand is there's not just one way to do it. You have to break all cubic equations into a bunch of different categories, and then each category has its own set of factoring rules. And it must be really complicated because they don't teach it to anybody. They only teach us one way, and then they teach us a workaround that allows us to do the same job with less effort. Not less effort, but you only need 2 possibilities. Actually, you only need 1. So I will teach you a way to find the roots of that, but we're not going to use factoring to do it. Except there is one really easy case called factor by grouping, which if you have a binomial like x squared plus 6 times a binomial x plus 3, so you have a quadratic equation that only has 2 terms, and then you have a linear equation. If you multiply those together, then you can do what is called factor by grouping. Most of the time it doesn't work. So to factor by grouping, you group this, and you group this, and you pull out the greatest common factor of each. So x squared, and I'm left with x plus 1. And then what's the greatest common factor of the other? Now I could pull out 4 or negative 4. Why do I want to pull out negative 4? grouping won't work otherwise. So if I pull out -4, now I get x plus 1. And grouping only works when this and this are identical. If they're not, you cannot factor by grouping. And most of the time, you cannot factor by grouping. The only time you can factor are in these pre-contrived equations that they've built specifically to allow us to factor by grouping. Well, now I have essentially two terms. I have this, and I have this. What do those two things have in common? X plus 1. So I'm going to yank out the factor x plus 1, which seems a little weird, but it's perfectly allowed. And I get x plus 1, and then I'm left with x squared minus 4. Do you see how contrived that is? Grouping only works when you have a quadratic equation missing its middle term multiplied by a linear factor. And now that quadratic equation is a difference of perfect squares. So I get x plus 1, x minus 2, x plus 2. So my factors are plus or minus 2 and -1. Kind of a neat little trick, but in the next chapter, when we're solving bigger quadratics, we're not even going to check to see if they factor by grouping, because it's so rare we just don't even bother with it. Okay, that's it.